Good morning, Kyle.
Good morning, ma'am. Good morning, ma'am.
Good morning. Good morning, everyone.
Good morning. Hello, am I audible?
Yes, ma'am, you're
Yes,
audible.
yes, yes, yes.
A warm and graceful morning to our most valued guest of honor, esteemed speakers, worthy teachers, and participants. On behalf of Department of Chemistry, St. Xavier's College, Mumbai, I, Dr. Abhilasha Jain, Assistant Professor Chemistry, extend a very warm welcome to our resource person, Dr. Anurag Gaur and Dr. Premchand S. Jain. I also welcome our chief guest, Dr. Ravindra Deshmukh, Mr. Marwan Kotwal, Head of the Department of Chemistry, our colleagues from different departments, and all the participants to this RUSA-sponsored two-day workshop entitled Know Your Molecule Through Sophisticated Instrumentation Techniques. Before we begin with the procession, we request the participant to please note some points for the smooth conduction of this workshop. Kindly mute your microphone and turn off your video during the workshop to prevent any technical glitches. The workshop is also streaming live on the YouTube and the link for the same is given in the chat box. Please do not post any welcome messages in the chat box. Send your question for the speaker using the chat box or YouTube comment box only, and we will moderate towards the end of each session. In case of any technical issue, please post in the chat box. After each session, we will conduct the poll and the participants are required to answer the poll question. In order to get e-certificate, participants need to attend all the session over the 2 days and need to fill feedback form. Link for the same will be posted in the chat box and YouTube comment box at the end of the workshop. No link will be shared via email. Please don't post any query regarding feedback form link and certificate in the chat box. To ensure a smooth transition of this workshop, these instructions need to be strictly followed. We are hoping cooperation from participants and enriching workshop with you. In this technology-driven world, there is a high demand to fabricate new material for the different purposes in different fields. New compounds and catalysts need to be synthesized. By characterization techniques, the molecular structure and properties are probed and measured. It is a fundamental process in the field of material science, without which no scientific understanding of molecule could be ascertained. And thus, the characterization of molecule become a very essential part of the research. While many characterization techniques have been practiced for centuries, new techniques are constantly emerging. In particular, the advent of the electron microscopy, advanced XRD, thermal method, and hyphenated chromatography techniques have brought revolutionary changes in this field. The aim of this workshop is to give exposure of these sophisticated instrumentation technique and explore the application of these technique in different fields. Light and brightness have always been equated with positivity. Though we are conducting this workshop at online platform, but we will have our traditional auspicious lamp lighting ceremony as a tribute to Ma Saraswati. I request Ms. Neha to proceed the lamp lighting ceremony behalf of us, followed by our college anthem. Neha, over to you.
Yes, ma'am.
शुभं कुरु त्वं कल्याणम् आरोग्यं धनसम्पदः शुभं कुरु त्वं कल्याणम् आरोग्यं धनसम्पदः शत्रुबुद्धिविनाशाय दीपज्योतिर्नमोऽस्तु ते दीपज्योतिर्नमोऽस्तु ते शुभं कुरु त्वं कल्याणम् आरोग्यं धनसम्पदः सम्पदः शुभं कुरु त्वं कल्याणम् आरोग्यं धनसम्पदः
Thank you, Neha. Now we'll be playing our college anthem. Over to you, Neha.
You gave me roots and wings, Saviors. Open my eyes to things, Saviors. Somewhere along the way, you taught me how to fly and how to stay. In a world outside so differently, Saviors, you helped me become more me.
Fly like an eagle, discover new skies. With wings we've been given to soar ever high. Over mountain and ocean beach, learning from what they teach, believing that we can reach way beyond. Saviors,
You gave me roots and wings, Saviors. Open my eyes to things, Saviors. Somewhere along the way, you taught me how to fly and how to stay. In a world outside so differently, Saviors, you helped me become more me.
to walk over rough roads, to open our minds, to ask the right questions and answers to find. Even though we stand alone, we know that we have grown, all because you've shown skies beyond.
Saviors, you gave me roots and wings, Saviors. Open my eyes to things, Saviors. Somewhere along the way, you taught me how to fly and how to stay. In a world outside so differently, Saviors, you helped me become more me. You helped me become more me. You helped me become more me.
Thank you, Neha. To conduct this type of event, the encouragement is very essential. I'm happy to say that we have one such personality, Dr. Ravindra Deshmukh, with us, who is the source of inspiration and motivation for us. Dr. Deshmukh has served as principal Konkan Gyanpith Karjat College of Arts, Science and Commerce for more than 14 years. He also served as chairman, Board of Studies Chemistry, University of Mumbai. He has published 15 research papers in highly reputed journal in field of synthesis and characterization of transition metal complexes. With this small introduction, now I would like to invite our guest of honor, Dr. Ravindra Deshmukh sir, to address the participant. Over to you, sir.
Sir, please unmute yourself.
Yeah. Hello.
You are audible.
Yes,
You are
sir,
audible.
audible.
You are audible.
Yeah.
Sir.
Yeah. Okay. Fine. So thank you, Xavier's, for inviting me for the inauguration function of this very important and very relevant workshop that you have organized at the right time, uh, given the COVID situation and the difficulties that all of us are encountering in the field of academics and research and development and whatnot. Uh, you have always been, your institution has always been to the forefront and rising to the challenges posed by any situation regarding academics and quality in academics. So I congratulate all of you for organizing this wonderful event. And I'm absolutely certain that the participants will be enriched after this 2-day workshop regarding molecules and their relation with the instruments. Uh, should I formally declare this workshop as open? I hope, and then
Yes, sir.
yeah. So I welcome all participants to this workshop and declare this workshop as open. Now, regarding a very small talk that I would like to make on this occasion. The theme of the workshop is about instrumentation, the role of instrumentation in knowing our molecules. I remember the days when I was a student in the 70s or late 70s, when to measure potential EMF of a given cell, we had to construct the voltmeter using the Pogendorf's compensation principle. There used to be a huge 1 meter scale, and all those electrical connections we had to make. That we had to get them assessed by our teachers, demonstrators, and after that we could proceed with the experiments. So from that time to the present times, when very sophisticated and easy to use instruments are available in the laboratories, it's a great achievement for all of us. The role of instrumentation in analysis can never be overrated. The first instrumental analysis, as we can talk about it in terms of analytical chemistry or instrumentation, was perhaps used for the discovery of elements, rubidium and cesium, somewhere in 1860 by Bunsen and Kirchhoff. From that time in 1840 till now, when we have very sophisticated spectrophotometric instrumentations of all type, uh, it's a great progress that we have made. Regarding the other instruments that are going to be discussed in these workshops, the one that comes very easily to my mind is about the X-ray diffraction studies and the X-ray diffraction instrumentation that is going to be talked about. It's very interesting to note that there are about 25 Nobel Prizes assigned to work related to X-ray diffraction. From the first time when X-ray diffraction was used in analysis, somewhere in 1912, when von Loo gave his equation regarding X-ray diffraction by crystals. From that time till today, there are about 25 Nobel Prizes, out of which 19 are in the subject of chemistry. So that can easily be taken to highlight the use and application of X-ray diffraction, ranging from the size of atoms to the lengths and types of chemical bonds, structures of biological molecules, their functions, biological functions, designing pharmaceuticals, and so many related aspects. It has revolutionized the way we learn chemistry. It has revolutionized the way we understand chemistry. If mathematics, it's often said that mathematics is a queen of sciences, then I tend to believe that chemistry is a central science. And if chemistry is a central science, then analytical chemistry strengthens chemistry in its outreach programs. The instrumentations that are used in analytical chemistry that take chemistry to the various other fields like biology, life sciences, and so on, including even physics and astrophysics and whatnot. So it's a great value that instrumentation has added to the learning and understanding of chemistry. I hope that today's workshop, will really enrich all the participants. There are excellent speakers, as I see Dr. Jain and Dr. Datar, both great people. They have done great work in their own fields, and I'm absolutely certain that participants will have something good to take away from this workshop. I once again congratulate all of you for arranging this workshop, and I hope that I also can find time in these 2 days to attend some of the sessions uh, that will be conducted in this workshop.
Thank you, sir, for addressing the participant and motivation. In very concise and effective manner, sir has highlighted the significance of these technique. Now I invite Dr. Geeta Kotian, Vice Chairperson of this workshop, to introduce the first speaker of the day. Over to you, Geeta ma'am.
Thank you, Abhilasha. Good morning, everyone. I would like to introduce Dr. Anurag Gaur. Dr. Anurag Gaur is from the National Institute of Technology, Kurukshetra. He's Associate Professor in the Department of Physics. Dr. Anurag Gaur did his PhD in the year 2007 from Indian Institute of Technology, Roorkee. His research interests are green energy production and energy storage of materials and devices, multiferroics materials, and functional nanomaterials. His current research work is in design and fabrication of hybrid supercapacitors, hydroelectric cell, and utilization of waste biomass for energy applications. He has guided 7 PhD students, and currently he has 4 students doing PhD under him. He has also guided 50 MTech students. To his credit, he has 77 international publications, and he has filed 2 patents. He has received several grants over the years from government organizations such as DST and CSIR. Dr. Anurag Gaur has received the Best Teacher Award from NIT Kurukshetra in 2019. He is the editor of journals such as Scientific Reports and Applied Science Letter. He is listed in Mark's Who's Who in the World in 2011 edition as a distinguished achiever. Marx is US-based magazine. I now invite Dr. Anurag Gaur to deliver his lecture. Thank you.
So good morning, everyone. Am I audible to all?
Yes, sir.
Okay, so first
Yes,
of all,
yes.
yes. Thank you so much for giving me the opportunity to interact with all the participants. They are attending this 2 days program related to the to know your molecules. So today talk we will discuss about some of the microscopies. So as the topic of this talk, it is related to know your molecules. So naturally the molecules, we know that atoms and molecule size, that is into the nanometric or atomic dimensions. So it is very important that what are the instruments, techniques that is being used to see these smaller length of the scales. So for that, among these techniques, so that is the transmission electron microscopy, electron microscopies. So we will discuss during the presentation of the talk I will deliver today. And so just I share my screen. So I hope that my screen is visible to you. Okay.
Yes, sir.
So we will start with some historical prospects about the microscopies. So all we know that in 1924, the de Broglie that give this concept, electron beams, electron moves in a beam, it present the wave nature. And by utilizing this concept in 1931, that was the German scientist Max Knoll and the Ruska, they built the first transmission electron microscopy in the Berlin. So it was in 1931. Some development has been made in this transmission electron microscopy. Then SEM was invented in 1941 by again the German engineers. And then in 1981, the scanning tunneling microscopy was invented. And after that, there is a lot of development are going on in these electron microscopy, scanning tunneling microscopy, and transmission electron microscopy. So their size is reduced, their resolution is improved year by year. And you all know that nowadays, we have the resolution even less than to the atomic level. So we can see our atoms, we can realize atoms. So as this is the title of this workshop, that to know your molecules. So naturally the molecules play, because the every material is made by the atom. So atom is very important, and how these atoms are arranged, it matters, and accordingly the property of materials are changed. So I can just quote one example, that we know the different allotropes of the carbon is present in different forms. It present in forms of the graphene, it present in forms of the graphite, diamond, coal, nanotubes. So all these are the carbon allotropes, but you can realize that how much is the difference in the properties of these materials. One side coal, another side is the diamond. So if we see in these two material, either this is coal, either this is diamond. So both of the materials have the carbon atoms, but you know that how different are the property. Coal, this is a blackish material, and this diamond, it is a very highly transparent material. Coal is very cheap material, diamond is a very costly material. So important is that if both of them carbon atom, that what is the difference, why that is the difference in the property, is basically the arrangement of the atoms, arrangement of the molecules, that matters. The structures they are having, what kind of the bonding they are forming. So it will properties. So it is very interesting, very important to understand that about our atoms and molecules. You all know that the nanotechnology concept, it was started in, once there was a lecture is delivered in 1949 by the this concept that if we can manipulate atoms and molecules, then we can change the property of the materials. So after that, lot of discussion going on, and people start working on these nanomaterials. So once the people have been starting to understand that how the atoms, molecules, we can change their positions. So if we are able to do that, suppose we can take the carbon atom from the coal, and if we could arrange them as per the structure of the diamond, so we can convert coal into the diamond. So, but only thing is that it is not so easy task. You cannot, the atoms is not like the simple bigger balls that you can pick them with by years and could arrange them as per the structure of the diamond. So convert coal into the diamond, but importance is that firstly we should be able to handle the atoms and molecules, because the length scale is very smaller. You can realize the atomic scale. This is the 10 to the power minus 10 meter. So it is a very smaller length of the scale. If we can realize this smaller length of the scale, that the thickness of the human hair is 10 to the power 6 times more thicker as compared to the 1 angstrom level of the size. So this is very small length of the scale. So naturally we need some instruments, some techniques. By that we can only handle the atoms and molecules. We cannot handle them by the hands. They are only handled by the certain sophisticated instrument and techniques. So therefore, this all field of this nanotechnology is emerging because of the realizations of the atoms, molecules, their positions, their morphology, their arrangement, their crystal structure. So that all play the role for changing the property of materials, and accordingly we can utilize them for the different applications. Now the question arises that how we can see these atoms and molecules. First thing is that how we can see them. The first target is how we can see atoms and molecules. Then it will be the next target is that how we could arrange them as per the structures what we want. Suppose we have to make a desired structure, so we have to arrange these atoms in a particular pattern. So what kind of techniques we require, that is the second task. So first thing is that we have to see them, we have to realize these structures. So we have to come for that. The scanning electron microscopy, they are being used to see the atoms, to see the molecules. So that we start with the limit of resolution. So limit of resolution is that for our eyes, though, that the limit of resolution is 0.1 mm. So that is our naked eyes without using any lens or any aid. Our eyes, they can have the resolution of 0.1 mm. Means the 0.1 mm distance object can be seen clearly, or either they can be separated clearly. So that is the limit of resolution of our eyes. But for the light microscope, everyone you have been seen in your biological labs and all that. So these are optical microscope, means the light microscope, and their limit of resolution is 0.4 micrometer. So that is the limit of resolution for these light microscope. So because this limit of resolution by the optical microscope, we cannot see the atoms and molecules. The minimum size that we can see by the optical microscope, that is the 0.2 micrometer. So beyond to that, the smaller size, we cannot see by the light microscope. It means by the optical microscope, we cannot know our molecules, we cannot see our atoms. So then we have to go for the scanning electron microscope, or either the electron microscope. So because the resolution, it depends upon the wavelength. So wavelength, as much as the wavelength is smaller, the resolution will be better. So we have to think out that how we can reduce the wavelength. So for that, this approach, we have to move towards the electrons, because we can change the wavelength of the electrons. Suppose electrons are being produced by some method like the thermionic emission, and you will apply some accelerating voltage to move these electrons in a beam form, and then it will have the wave nature. So it will have some wavelength. So that wavelength is depending upon that how much voltage you are applying, accelerating voltage you are applying. So it will decide the wavelength of these electrons. So you can see with this formula, lambda is equal to h upon root 2 mev. So where v, this is the accelerating voltage, h, this is the Planck constant. You everyone know this. It is by the Planck. This is the de Broglie equation. So this is Planck constant h, and this is the mass of electron. E, this is the electronic charge, and v, this is the accelerating voltage. So as you will increase the accelerating voltage, the wavelength goes down. So by that way, if we want to improve the resolution, we have to minimize the wavelength. So that is the equation, lambda is equal to root 1.5 upon v. You can directly get the wavelength in nanometer. So suppose, for example, we apply the 5 kilovolts accelerating voltage for the emitted electrons. So their wavelength will be 0.173 nanometer. And if we apply this voltage 10 kilovolt, then the wavelength will be 0.0122 nanometer. If we apply 200 kilovolt of the accelerating voltage, then wavelength is 0.0027 nanometer. So this is a very, very smaller wavelength. And as compared to the light wavelength, everyone know that it is 400 to 700 nanometer. So as compared to the 400 nanometer, this is only 0.0027 nanometer. So this is the region electron microscopes, they have the better resolution. Means we can see beyond to the 0.2 micrometer, means less than to the 0.2 micrometer size by using the electron microscope, because we can change the wavelength of electron by increasing the accelerating voltage. So that is the concept of that, why the electron microscopy, they have the better resolution to the optical microscope. So generally for seeing the biological things, bacteria and all that, we use the light microscope because they have the resolution up to 0.2 micrometers. So generally the bacteria's size, that is in micrometric range. But if we want to see the objects like atoms, molecules, and some other atomic planes, so naturally we have to move towards the electron microscopy, because they only have the resolution of this much smaller length of the scale at atomic. So how much is the resolution for a scanning electron microscopy? This is 1 nanometer. So 1 nanometer, it is that equivalent to the 10 angstrom. So we can see this much resolution by a scanning electron microscopy. While the transmission electron microscopies, their resolution is 0.1 nanometer. So you could see that 0.1 nanometer means it is that 1 angstrom. So we can have this much high resolution for the electron microscopy. So that's why they are being used to analyze atoms, molecules, to realize, to see them with help of these electron microscopies. So for that, the first time, you know that already, that the transmission electron microscopy, this was the first type of electron microscopy that is being developed, and it has the same principle as into the light transmission microscopy. But only difference is that in this microscopy, we use the electrons instead of the light. Otherwise, the principle is same. We are using the different lenses to focus the electron beam. And then there are some other objective lenses and the projector lenses. They will project the image of our object on the screen. So naturally, what is the thing in any microscope? They have to magnify the image of any sample. Means suppose you have a very small sample and you are seeing that with help of any microscope. So what they are doing, they are enlarging their image. They are magnifying their image. So once it was very smaller, our eyes were not able to see them because it was less than to the 0.1 mm. So then what happened? We will enlarge the image with help of the lenses. It will become bigger and bigger. So how many times we are magnifying the image? As much as it will seem bigger and we are able to see them. So that is being done with help of the microscopes. They magnify, because you cannot change any microscope cannot change the actual size of the object. Actual size, whatever, it will remain. But only thing is what they are just magnifying their image with help of the lenses. And once it will become magnified, it will be larger image. So we were able to see them. So that was the same principle is being used in the transmission electron microscopy as was in case of the optical or light microscope. But only difference was that we are using electrons instead of the light. So because the light electron wavelength was less, so therefore the resolution of the transmission electron microscopy, it was less. The resolution was better. So the electron microscopy, that basically this is an instrument where we use a beam of highly energetic electrons, and that beam is being interact with your sample. So then the different kind of the scattering of electron take place, transmission of electron take place, and then these scattered or transmitted electrons, they are being used to generate the image of our object. So two different types of the electron microscopies are popular. One is the transmission electron microscopy. This transmission electron microscopy, that is basically used to study the inner structures of the objects. If you want the information inside from the material, that what kind of defects is there, what kind of the implantation of the atoms and molecules is there inside a material. So that kind of information, it comes from the transmission electron microscopy. So it will give you the inner structure information. But the scanning electron microscopy, that give you the surface information. It give you the surface morphology and the macromolecular aggregation of some atoms at the surface only. I will tell you that why only the surface. So the transmission electron microscopy, it give you the inner structure information, because naturally you can understand even by that name, the electrons, they will transmit through the sample. So naturally they will completely penetrate to the sample. It will be the electron transparent should be the sample that the beam could be transmitted. Then so naturally it give the inner information about the sample. But in scanning electron microscopy, we don't use the transmitted electrons. We used only the scattered electrons. They just come from the surface. So we get the information from the surface itself, that what kind of the molecules they have, what kind of grains are there, what kind of the particles are there, what is their orientation, what is the shape of these grains. So shape may be different, it may be spherical, fiber form. So the shape, you can see that what kind of shape they are having, as well as you can measure their size, what is the size of the particles, what is the size of your grains, either there is any defect, cracks on the surface of the materials. So that kind of all information you can get through the scanning electron microscopy. So these are some of the image of the material. This is the budding yeast cell, and these three images are captured by the different microscopies. This is the light microscopy. This is the transmission electron microscopy. This is the scanning electron microscopy. So you could see that we get this image from the optical microscope, but you see that this with this optical the microscope, we are seeing that what is the shape of this cell, but we are not able to see that what is actually inside this cell. So inner structure we are not able to see. So that is only can be seen by the transmission electron microscopy. So thing is that as the resolution will improve, so you will have the additional feature. You can see the additional features, because if you are at micron level, so you just have seen that it is like a ball. But what is there inside this ball, you cannot see that, because your maximum resolution is in the micron range, and the size of this ball, it is in micron, or the grain, it is of the micron size. But if there are some nanometric structures, or there are some atomic level structures, so you are not able to see them until you don't have any microscope, their resolution is in the range of atomic and molecular. So therefore, you can clearly see the difference in this this compound microscopy image or this transmission electron microscopy image. It is just giving you so that kind of some cells are there. They are having this spherical shape or oval shape. But what is inside these cells, it cannot be seen by this compound microscope. It can be seen only by this transmission electron microscope. You can see inside that what kind of structures are there. You can realize their RNA, DNA, everything. So that is the more and more information you can achieve as you can get it. You simply that suppose we see the leaf of any plant. So we are just seeing that it is a what kind of symmetry is there. But if you can see the scanning electron microscopy of the leaf of a plant, so you will find that naturally there are some structures. Already there are very, very beautiful atomic level structures are formed, because ultimately thing is that every material start forming from the atomic level. Atoms start attaching to each other. They are starting attaching to each other and they are growing in all three directions. Accordingly, materials elongate and it get a big shape. So, but thing is that either we are able to see, we have any microscope that we can see that atomic structures. So even in the leaf of a plant, if you can see that, you can see that they will have a very, very beautiful structure. For example, that everyone we know that lotus leaf. So lotus leaf, you know, it has the water repelling property. If you put the water on the lotus leaf, it will not stick. It have the hydrophobic nature. So earlier that people see that yes, it was that the lotus leaf have the hydrophobic property. But why this lotus leaf have the hydrophobic property? It was not clear, because we have not seen that what kind of structure is there over the lotus leaf. So once people have been analyzed through these electron microscopy, the lotus leaf, then they have found that there are a very beautiful nanostructures over the surface of the lotus leaf. Even if you will touch the lotus leaf, it is not a very smooth. It is not very smooth. It will have some rough kind of the structures. So you can analyze them if with help of electron microscopy, then you will find that there are some very, very nanometric dimensions, the very fine spikes over there. And because of these spikes, they are increasing the contact angle, and contact angle will be very large. So because of that, they have the hydrophobic nature. So naturally, something is there, some region is there. Whatever exists in this universe, there is some region behind that why this happening. But thing is that either we are able to understand them, either we are able to give the explanation of that region on the concept of the science. So that is the important aspect for this. So that is the region that why that we have been find out that why the material have the different property. It must have some region, but only thing is that we have to analyze them. So naturally we have to need some instruments, some sophisticated techniques that will give you the idea that this particular material is having this specific property. So naturally it has some region. Only thing is that we have to explore that what is the region for showing this specific property. So region you will found only once you will have some techniques, once you will have some any methods, by that you can give the explanation that why this material is showing this property. So similarly, if we have this TEM image of this cell, so naturally we can give the more analysis rather than to having this optical microscope. So we can define all these inner structures and give the explanations of that. So this is the region that the better resolution microscope give you the better informations, better features, then you are able to give the better explanation of your material, device, cell, whatever you have. So this is same picture. So same again that we have told in the starting that TEM resolution is the best among these three, that even the TEM is having more resolution. I will tell you later why the TEM has the better resolution to the SEM. Again, because we need the high voltage is applied in the TEM, because the electron beam has to be transmitted across the sample. So you need a highly energetic beam, and highly energetic beam, then you have to apply a very, very high voltage. and this voltage is very high, so naturally the lambda will be smaller and your resolution will be better. Similarly, this is the E. coli bacteria image. They are captured from this compound microscope, TEM microscope, SEM, scanning electron microscope. So again, if you will focus them, you will find that the TEM images, they are having the better structures, better, more information rather than to the optical microscope. So thing is that importance is that resolution, because suppose we don't have the better resolution. So whatever we will see, we will say, okay, they are ball kind of the structures. But suppose this is the SEM image of the blood cell. So if I have only the micron size of this microscope, so we will just see it like a ball. But if we can have the better resolution, then we will find that even on the ball, there are some molecules are attached on the surface of it. So we can give the more information, and it will give the more explanation for the properties or the whatever region that the specific property they are showing. So this is the TEM image of Golgi complex, mitochondria. So definitely they are, the more features are being seen, that these are the blood cells, that what kind of structure they have. This is the Drosophila eyes. So you can see that what kind of beautiful symmetric structures are over there. This is the pollen grains images. So you see that how kind of that, what kind of hexagonal structure of there over their surface. And these are very fine spikes are there. So that information you can achieve if you have the better, resolution microscope. It will give you the more and more features, and you can have the better explanation of your results of your analysis. So this transmission electron microscopy, that is a very important tool in the material science. You know that, because, and what is there? A highly energetic beam of electrons that will interact with that will pass through a very thin sample, and the interactions between the electrons and atoms that will give about the features in the structural dislocations, grain boundaries, even the chemical analysis can be performed. So this TEM study, it will also used for growing the different layers. So if you are growing the multi-layers, so you can measure their thickness as well by using them. You can get their composition also. You can get some, if there are defects in semiconductors, if you have been implanted some of the atoms or ions within the material for getting some specific property, so that also can be done. And the high resolution images of the material, you can see the shape, size of your grains or particles, density, and everything. It can be seen on the surface morphology related to from the materials through these electron microscopy. So as we told that electron microscopy, their resolution is high because their magnification is up to 2 million times. Means up to 2 million times they can magnify the image. So, and in the light microscope, they can only 1,000 to 10,000 times. So naturally, the electron microscope magnify more. So naturally, we are having the better resolution, and we can see the very, very smaller structures with help of the electron microscope as compared to the optical microscope. Now the things comes that SEM, is it like a TEM? Means the behavior, the principle of working of the SEM is like a TEM. So the SEM, there are several electromagnetic lenses. You know that electron gun will be common in both, either it is SEM or TEM. So there will be the electron gun, and electron gun job is that electrons will be produced, and then these electrons will be accelerated. They will come in the beam form. So that is the job of the electron gun. So once these electron beam is formed, so there are several electromagnetic lenses, condenser lens, objective lens. So these electromagnetic lenses, they make the electron probe formation, means electron beam being focused, and then this electron beam will interact with the sample. So there is a difference in the working of SEM and TEM. In TEM, that I told you, it works like an optical microscope, that this electron beam, it will be focused and it pass through the sample. Then it will project the image of a fluorescent screen. So directly image is being projected, or either you can see that image by the eyes, or you can capture this image by the CCD camera. But in the scanning electron microscopy, we are not projecting the image. What we are getting the backscattered electrons and the secondary electrons. So these scattered electrons, and they are coming from the surface of the material, they are being detected using the detectors, and these detector signal they being amplified, and then through the CRT tube we can get the image of the sample. So that is the difference in the working principle of that, in the scanning electron microscopy and transmission electron microscopy. Now we see that the electron beam and specimen interactions. So we have this incident high energy electron beam, and this high energy electron beam, it will interact with our sample. This is it will fall over the sample. So once it will fall, that some of the electron they being scattered from the surface, and some of the electron being transmitted. And so during this scattering from the surface, different kind of electrons are produced: secondary electrons, characteristic X-rays, and then backscattered electrons, OJ electrons. They comes from from the surface, and those electron beam, they are being transmitted. So these transmitted electrons are being used in the TEM. So we can see here that in the scanning electron microscopy, we use these backscattered electron and secondary electrons. They are being used to generate the image. But in the transmission electron microscopy, we use these transmitted electrons. So naturally, if you are using the TEM, so your electron beam should transmit it across the sample. So that is very important, that the thickness of the sample should be less, so that electron beam could transmit across the sample. So naturally, the energy of the beam, electron beam, it should be very large in case of the TEM. Then only the electron can be transmitted. Otherwise, all they will be scattered from the surface. They will not get transmitted. So if it's not transmitted, you will not get any signal. You cannot get any image in the TEM. So this is important, that the energy of the transmitted electron beam is very large. And how it will be large? You will apply a very high accelerating voltage, and naturally once the accelerating voltage is very, very high, then the wavelength will be very, very smaller, and the resolution is also better in case of the transmission electron microscopy. While in this scanning electron microscopy, there is no issue of the thickness of the sample. Whatever is the thickness, it does not matter, because we are getting these backscattered and secondary electrons. They are being used to generate the image. They are just coming from the surface. They are not very deep from the sample. They are coming from the surface. And how much depth is there? You can see with this picture. So that is the primary electron beam. And that is the upper surface of your sample. And that is the depth is being shown. So from the very just surface comes the OJ electrons, and OJ electrons, they come from the 5 to 7 angstrom. This is the thickness. So they are totally from the top of the surface. OJ electron comes. Then the secondary electrons, they come from the depth of up to 10 nanometer. So they are just coming from up to the depth of the sample of 10 nanometer, and the backscattered electron, they are maximum up to the 100 nanometer. So the information, whatever you are getting through the scanning electron microscopy, because we are using only the secondary electrons and backscattered electrons, we are getting the information only from the surface, or maximum from the depth of 100 nanometer, not beyond to that. While in transmission electron microscopy, because the electron beam will transmit it through the whole depth of the sample, whole thickness of the sample. So you will get the inner structure information from the transmission electron microscopy. While in the scanning electron microscopy, we got the information just only from the surface. So that is important, that what kind of information comes from the SEM. and it comes from the surface. Surface information basically comes for the scanning electron microscopy, while in transmission electron microscopy, we can get the inner structure information as well, because in SEM, we use the secondary electrons, backscattered electrons for getting the image, while in transmission electrons, we use the transmitted electrons for obtaining the image of the sample. So that again we can see that electron amount and that their energy in terms of the energy of the signal electrons. So the secondary electrons, they are having the energy up to the 50 electron volt, and beyond that they are the backscattered electrons. Their energy is greater than to the 50 electron volts. So we have the different detectors, and you know that because there is a difference in the energy, so we cannot use a single detector to detect the backscattered electrons and secondary electrons. So separate detectors are being used in the system. There will be one will be a secondary electron detector, another will be a backscattered electron detector. So they will capture as per their energy these different range of energy range of the electrons, and then they are being used for generating the image. So you see that this is the light microscope and the transmission electron microscope. So in light microscope, you know that there will be some lamp will be there. It is a source of light. It will illuminate, and then it will with the help of some condenser lens, this being focused on the specimen, and then it will be transmitted through the specimen, and after that there will be the objective lens. Their image will be projected, and we can see with this eyepiece of this microscope. So as similar, we use the same principle in the transmission electron microscopy. Here will be the electron source, that is electron gun. That gun will emit the electrons. Then these electrons will come into the forms of a beam by applying accelerating voltage. Then with help of the electromagnetic lenses, this beam is being focused. And after focusing this beam, it will pass through this the specimen. It will transmit through the specimen. And these transmitted electrons, they will be with help of the objective lens, we can generate their image. Projector lens is also there. We can switch, either we can get the imaging formation or the diffraction formation, and then this image is being projected over this fluorescent screen. So this screen image will be here, and you can see that, watch that by your eyes, or you can capture this image. There are some CCD camera are attached with the system. Image will be captured and it will be visible over your computer, or you can see the image. So that is the working of TEM. It is almost similar to the light microscope. Only difference is that in light microscope we are using the light as a source of, but here we are using electron as a source. But naturally, this is the image captured by a light microscopy, electron microscopy. So resolution will be better. You can see that optical microscope resolution is not as good, because resolution better means their features will be very clear. The small dimension features, their edges will be shown very clearly. So you can see the difference in the image of this one and this one. It is a more clear image with the more information is available, and by capturing the image through the TEM. So because the thing is that magnification is better for the TEM as compared to the optical microscope. So this is the layout of a transmission electron microscope. So basically there is a beam of the electrons, that the electron gun is there. This electron gun, it will generate, there will be some filament is being passing some current. So it will, through the thermionic emission, it will emit the electron, and these electrons are coming one by one. So as per the de Broglie concept, electron is a particle, but once it is being start moving or accelerating, it have the wave nature. So to make the wave, to make the beam, we will apply some accelerating voltage at the anode here, and then it is accelerated, it comes in the beam form. So how much is the voltage over this anode? So naturally it will be high voltage, so it will be, the wavelength will change. So that wavelength matters because it will decide the resolution. And then it will be the condenser lens, it will just focus to these highly energetic electron beam. Then it will pass through the specimen. And it is important the thickness of the specimen that this electron beam, it must transmit it. If no transmission, so you will not get any image over this screen, fluorescent screen. So it must be transmitted from here. And after the transmission, this there are some objective aperture. Objective aperture is basically that it will stop some the high angle electrons, otherwise the image will be blurred. So that and then objective lens, it will project the image over this, and it is further magnified with the projection lens, and this image is being projected over this fluorescent screen, and then we can see the image. So this is basic working, and then the beam that strike the specimen, it is part of this transmitted electron, and it depend upon the thickness as well. So the electron transparency of the specimen is very important. If it is not electron transparent, so the very less amount of the light will transmit it, so then you will not get a good image. So this transmitted portion that is being focused by the objective lens into an image on a fluorescent screen, and then with help of the CCD camera, the charge coupled device, you can capture the image, and that image could be utilized to further analysis of that sample. So this is the working of this transmission electron microscopy. So if we see that what are the different component of this transmission electron microscopy. So first thing, this is the electron gun. This is the electron gun, and this is it. What is the job of the electron gun? It produces the high energy, high current, highly coherent electron beams. And then there are some condenser lens. These are the condenser lens that the control the spot size. Spot size is also important because the electron beam is coming. So we have to make it as much as fine. It should be highly focused. So with help of the condenser lens, we have to make it highly focused. We have to minimize their spot size, and then it will illuminate on the sample. So the objective lens, the image of the sample is being produced, and then there will be a projector lens that with help of this intermediate and projector lens, we can get change in the diffraction to imaging formation. So you see that with the transmission electron microscopy, we not only get the image of the sample, but we also can get the diffraction also. So we have to switch from the projector lens and intermediate lens, that either we want to get the diffraction image or either we want to get the imaging. So that can be, you can control there. And then finally the image that can be obtained for this transmission electron microscopy. This is the again thing that how the image is being projected with help of these again electron source, then condenser lens, it focus them, then it will pass through the object, transmitted, then objective lens. So there some intermediate lens. So they will decide either there will be an image or either the diffraction pattern. So you can just change the focal plane. So back focal plane, you can switch here from the intermediate lens and the projector lens, and accordingly the image or diffraction pattern of the sample can be obtained on the screen. So this is the column of this transmission electron microscopy. So this column is this is the outer column. So inside that there is a filament. So this filament, the electron source, and this consists of a cathode and anode. So cathode is basically tungsten filament is generally used, which emit electrons when this filament is being heated. So it emit the electrons, and there will be a negative cap confine these electrons in a loosely focused beam, and this beam is then accelerated towards the specimen by there is a positive anode, and this anode is at high voltage. So then this beam is formed. So this is the electron, this is the electron source or electron gun. So then there are these electromagnetic lenses are there. Electromagnetic beam is highly focused, and using this electromagnetic lens and apertures, then this is the sample holder is there. So this beam is being transmitted through the sample, and then this will again projector lens, they will project the image on this screen, and then on this fluorescent screen we can get the image of our sample through the transmission electron microscopy. and inside this whole column there will be a vacuum. And so we will tell that why the vacuum is required. So that is the thing is in transmission electron microscopy, there will be some sample preparation that is important. So as we know that in TEM, the sample should be electron transparent, means the electron beam that could transmit across the sample. So for that, there are some conditions that you have to prepare your sample first. So firstly, you make your sample thin. Their thickness should be around less than to the 100 nanometer. So then only the electron beam could transmit to that. So firstly, you have to make your sample thin. So there are the different ways you can make your samples. There are different mechanical grinders comes. So they just, you can have the grinders. So they grind your sample from one side. You can make it the thin, or either from the both side you can grind it, and not to the whole sample, but at least some part of the sample that will be at the center where the beam has to be passed. You have to make it very thin. Mechanical grinder you can use, sometimes chemically we can do it by the etching process and all that. We can make them the sample electron transparent. So in TEM, sample preparation part is tough. Firstly, you have to prepare your sample that it must be the electron transparent. So for that, you have to do the different things. Firstly, that sample, suppose you are making the thin films. So thin films, then it depends upon that how much is the thickness. If thickness is already very thin, you have to make the 10 nanometer thick and this kind of the film. So then there is no problem. But if the film is thick, it is in micron range. So you have to make them thinner first. You have to make them that you have to grind it, and or either you have to do the chemical etching process and all that, so that the electron beam could transmit them, their thickness could be minimized. So that is important. So different methods, different grinders, different system comes, they can make your sample electron transparent. So that is the cleaning, rinsing and staining is required to remove any heavy metal compound on the surface of the material. Dehydration is required, embedding, trimming of this and ultra thinning, sectioning. So that is required for the scanning electron, transmission electron microscopy. But in SEM, there is no need to do this. Their sample preparation, no required. Only whatever is sample, you just put it in your SEM chamber, because there no issue of the thickness. You don't need to transmit the electrons. Only electrons, they have to be scattered from the surface, and these scattered electrons, they will be used to get the image. So therefore, there is no issue with the SEM. SEM sample preparation part is very, 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 very easy, but just only you have to see the dimension, that whatever is the size of your chamber where you have to place the sample, it should not be the bigger than to that. Otherwise, you can put it over your holder. Thickness does not matter of your sample in case of SEM. But in TEM, thickness is very important. You have to minimize it, and so that the electron can be easily transmitted across that, and then you can get the image. However, some of the expert people, they can just do the analysis even without grinding if sample is thick. But that can be done only by the expert people. What they do, they just interact the electron beam at the edge of the sample, not from the center and all that. From the edge part, they just set your sample like that electron beam will go through at the edge of the sample. So naturally it will, once it is not, so it is at the edge, so it will be just pass through it, and some part of the sample is being interacted with this electron beam. So then you can get it. But it is very difficult that you have to handle your sample. There will be outside, you can have the control of your sample. You change their position, this. So, and you can bring the electron beam closer to the edge of the sample so that it could touch there, and then the image can be projected. So, but in general, we have to make the sample electron transparent. Then only we can get the sample by the transmission electron microscopy. So that is the case of if you have a thin films or some wafer, some layered material. But suppose you have the powder, then how you can perform the transmission electron microscopy? So for the powder, we use the grids, that kind of grids. These are the grids are there. So grids are like this, and you see that there are a very small size of the masses. These are the mass are being formed over here. So what happened that because if you are having the powder material, so you have to be attach your powder over these grids. So you can make some solution, and you can put you can disperse of your powder material in some liquid, and then you dip these grids also in this liquid and then take out. So some of the particle of your powder, they will stick over these grids, and then these grid will be placed as a sample, and then electron beam will pass through these grids. So grids are already electron transparent because they are mesh, they are having here the pores are there. So naturally they are electron transparent, and your powder sample image, those particles, they are being attached over the grid, their image can be seen. So you can see the image of your powder sample as well by using this approach, and then you can put the powder material also can be analyzed, their shape and size of the particles you can see with help of this grid, using the grid for transmission electron microscopy. So if we look about the advantage and disadvantage of the transmission electron microscopy, so this TEM, that is this offer a very powerful magnification and resolution, because to make the electron transparent, the beam should be very highly energetic. So the voltage is too high, 200 kilovolt, 300 kilovolt. So naturally the electron wavelength will be very less in that case, and resolution is very, very high. So TEM that give you the wide range of applications. It can be utilized in variety of different scientific, educational and industrial fields. So there are a lot of use of that in research, and they are being used for industrial applications. So TEM that provide the information on element, and it gives you the compound structure, diffraction pattern, and the images are of high quality. Even you can see the planes, atomic planes, you can see that with help of the transmission electron microscopy. If we see the disadvantages, so disadvantages are TEM is very large and expensive system. It's have around 5 to 10 crore, that is the cost of instrument. So it is costly, not accessible to all. And that laborious sample preparation part is tough for the TEM, but as compared to the SEM, it is very simpler. You can very easily make the, you can very easily put the sample as it is in the SEM, but in TEM, firstly, you have to bring it, you have to make it the electron transparent, then only you can use it. Third is the operational and analysis requires that special training, that how you can handle them. Sample limits is there, only limited kind of the samples are being used. So you cannot use like some the materials, they can be trapped in the column under magnetic field and all that. So you cannot, so that kind of some restrictions are there. And so this is the disadvantage, images are black and white. So now we come to the scanning electron microscopy. So this scanning electron microscopy, this is the picture of a SEM, that this is the geol SEM, that it is the column, and these are the detectors are being attached with this, and this is the chamber where the sample will be placed. So during the live demonstration, we will see that how the sample will be placed there. And this is the column where this whole part is that there is electron gun. There are some, these are some electromagnetic lenses. And so that, but in case of SEM, in TEM, that sample will be like in between here, because electron beam will transmit, and this transmitted beam will use to get the image. But here, the sample is at the bottom, and because after the scattered electron, they will be detected through the detector, and you can get the image on the computer screen, and you can analyze the sample. So this, if we see the comparison of this in the working, so we have seen that for this light microscope, and this is of the transmission electron microscope, and this is the scanning electron microscope. So it was the same that you know already, that this pass through it and the image is projected over the screen. But in the SEM, what happened? This is the electron beam that is being focused, and it interact with the sample at this place, and after the scattered, back scattered, and the secondary electrons, they are being detected by this detector, and after the amplification they are being sent to the CRT, cathode ray tube, and here the image of your sample will be formed. So this is in the difference in the working principle of the SEM rather than to the TEM. So now if we see the image of this is the image of a optical microscope, and this is the image of a, these are some fiber materials, and this is of the scanning electron microscope. So naturally you can see that SEM has a better image because resolution is better, and these fibers are very clearly seen. Their dimensions are very clear. So object size is very less for that. So natural resolution is better, will give you the more information through these samples. So the magnification that in optical microscope, they can magnify the image only 4 to 1000 times, but SEM, they magnify the image 10x to the 3 million times. So 3 million times they can magnify the image. So therefore resolution of SEM is 1 to 10 nanometer, while this is only 0.2 mm in case of the, this is for this, so that is in micrometer, not mm. Optical microscope resolution, that is in 0.2 micrometer. But in SEM, this is 1 to 10 nanometer. So that is the see this difference. Now the thing comes that what information we get from the scanning electron microscopy. So we basically get the information about the topological information. Topological means the surface morphology. Surface morphology means that what is the texture over the surface of the material, what is the grain size, what is the particle. Particle is what? It is again the collection of atoms. The grains is the collection of the particles. So ultimate thing is the atom. So the particle size means how many atoms are there in a particle. Suppose we are assuming that the diameter of a one atom is 2 angstrom. So in a 1 nanometer size of the particle, there will be around 4 to 5 number of atoms. So there may be some gap also. So naturally, and if you have a 10 nanometer size of the particle, there will be 40 to 50 number of atom. It will be 100 nanometer size of the particle. There will be 400 to 500 number of atoms. So it will depend that how many number of atoms they come closer to each other and they make a particle. So that is that will decide the particle. And then it is also important that what is the shape of your particle. Shape of the particle, it may be spherical, it may be cylindrical, it may be like a fiber forms, it may be a quantum dot form, it may be flower forms. So how this is all called the morphology. Means what is the shape of your particle and how it forms. It forming on that condition, atoms are attaching to each other and how they are growing. Suppose atoms are attaching to each other, they are growing in all three directions. So a bulk structure will form. If the atoms are attaching to each other, then they are growing only in one direction and two directions growth is restricted. So then they will make a wire form. It will make a fiber form. So in fiber, what is there? The cross section of the wire is very, very less as compared to the length. So it means atoms are growing across the length of this wire, but their growth is restricted across the cross section. Means in 2 dimensions, we have restricted the growth, only just growth is there in the along the length. So then wire formation comes. So it depends upon the energy conditions, synthesis parameters you are adopting, that either you can get the wire or either you can get the the spherical particles. So same material. Suppose we have the zinc oxide. So zinc oxide, I can grow it in fiber form, in cylindrical form, in platelets form, in spherical forms. So that is what is that? Their morphology is different. Material is same, material is zinc oxide, but their morphology is different. So because of that, it may also give you the difference in property. There will be change in the property by changing the morphology as well. So that is, so what kind of the morphology a sample have, it can be seen by the scanning electron microscopy. So that is the topological. Topological, we basically have the what kind of morphology they have. So in morphology, there will be two things, shape and size of the particle. What is the size? So size will decide how many number of atoms are there. It will decide the size. And what is the shape? Shape will be morphology. Either it is spherical, either it is dot forms, either it is the fiber forms. So that will decide the size. So this morphology of the material, this morphology of your sample, it also can be seen by the this scanning electron microscopy. Another thing, that is the composition. Composition is that what kind of which type of atoms are there inside your sample. So suppose you make the zinc oxide, so there will be some zinc atom, there will be some oxygen atom. So that kind of information, and in what is the ratio of these two. So in ZNO, they are in 1:1 ratio. In a 1 unit cell, 1 atom of zinc, 1 atom of oxygen. Suppose the material is BaTiO3, barium titanate. So in a 1 unit cell, there should be 1 atom of barium, 1 atom of titanium, and 3 atom of oxygen. So there will be 1:1:3 ratio for a BaTiO3 samples. So that is important, that the composition you have to be check out. That what, suppose I make the BaTiO3, so I have to know that either there are barium and titanium oxygen atoms, or either some other than also along with these three. So if they are, it means they are impurity in the sample, and in what ratio they are. Ratio is also important. Then only your compound will form properly. So that kind of information also can be get with the SEM by attaching a EDEX detector. Energy dispersive X-ray analysis, you can do it. And then you also can get it the elemental information along with the surface information like morphology, topography, and all this. So that kind of information you can also get with the scanning electron microscopy. Then crystallographic information, so that the texture is basically there. You cannot get directly measure the conductivity and all that, but you can see their texture. And on that basis, the explanation for conductivity and electrical properties, you can see that. Suppose you have seen the grain boundaries. So if the material have the large number of grain boundary, so what happen? Their electrical conductivity will be less because there will be more hindrance in the movement of charge carriers. So the conductivity goes down. So that kind of, suppose a material conductivity is decreasing and you are not able to find out what is the reason for that. So you can get it through these images and you can see that what is the size of particle. Either there are any cracks, either there are any defects. So if there are some cracks is there, if there are some defect is there, so you can give, they may be responsible for this decrease in the conductivity. Or the grain boundary number is large, so that may be the reason for having the low conductivity. So that kind of explanation can be given via the analysis of the image you are getting through these the scanning electron microscopy. So that kind of information we can get from the image that we get through the scanning electron microscopy. So now you can see that a look inside the column of a scanning electron microscopy. This is the actual image of a microscopy. So this upper one is the electron gun. This is the whole chamber. This is the whole chamber. Here is the electron gun. And this is the gun alignment control is there. So then this is the pneumatic air lock valve is there. Here is the condenser lens to focus this beam. Then the scanning coil, they basically control the movement of your electron beam. And then this is the this is the motorized state that this comes out. If you want to change the sample, then it will go inside the chamber, and then it will be aligned with the electron beam. And this, so this is the sample chamber. So within this hole, there will be a vacuum. So other side vacuum system is attached. Molecular pump or turbomolecular pump is attached. So the vacuum order should be 10 to the power minus 10 torr. So that is there. Then detectors are there. They will be used to get the image of the sample. So this is the picture of a scanning tunneling microscopy. So this is the inside view again, that this is microscopic column. So here this is the part of electron gun. So electron gun, this is the cathode. This is, and this cathode have a very special shape. This is the Van Alt shape, and so that the electrons, they come just one by one. They will not be highly scattered, so that they will come just one by one, and with the help of the anode, we can make them in a beam formation. And then these are condenser lenses there. So these are then the scan generators or scanning coils. They can make a small movement in the electron beam. And these are the detectors, scanning electron detector. This is the backscattered electron detector. So the output of this detector, it will send to a video amplifier. They will amplify the signal. Then they will pass through the CRT, and here over the CRT image will be produced. So this is the working principle of this scanning electron microscopy. So again, this outer one is the vacuum chamber. Vacuum is there in the whole chamber, whole column as well. Condenser lens, electron beam, objective lens, and this bottom part here is the sample is being placed, and then they are attached with this secondary detector at this end, and then backscatter detector. It not necessary both of them you may have. In some system you will get both of detectors, secondary and backscattered. In some case you will get only secondary electron detector. So that depend upon the system, and that it will generate the image of your samples. So as a source, I told you that electron beam source, so generally two type of source are used in these electron microscopy. So electron gun, that is used produce a fine controlled beam of electrons, which are then focused at the specimen surface. So these electron guns may either be thermionic or they are field emission based. So two types of the electron source we use. Tungsten thermionic source. So this is the simple and very fine tungsten wire we have here, and we pass the current over this, and by passing the current it will heat up, and thermionic emission, the electrons are emitted. These electrons are being accelerated by this by applying a voltage at the anode. Another is the Schottky field emission source. So by the field emission process, electron can be emitted. So this is a crystal which a very high voltage, and we apply here a very high voltage on the tip, and then the electrons are emitted. So these are the two processes where we use to emit the electrons, either thermionic source or field emission source. So this is thermionic emission gun. You can see that this is filament and all that. So we will apply a DC current so that the 2700 Kelvin temperature is produced. So we can use either tungsten filament for thermionic emission or either lanthanum hexaboride, LaB6. So these two filaments are used generally for this purpose, this LaB6 or this. So vacuum is there inside this column, and then these electrons are accelerated from 1 to 50 kilovolt. And in field emission gun, this is a very fine, the wire is there over this. It is a tip of tungsten kind of a needle, and that is made up very sharp. It is less than 0.1 micrometer. So this electric field at the tip is very strong, and we will apply a very high voltage here. So this high electric field we apply, and these electrons are pulled out from the tip by under the influence of this high electric field. So this is the field emission gun, and the probe diameter is less than 1 nanometer. So that is very important, that what is the diameter of your probe or the spot size of your beam. So that will also affect the resolution. So this is the field emission gun. So these thermionic gun or field emission guns, so there is some size of the spot size of your beam. This is for tungsten 50 nanometer, LEB 65 mm, and for the field emission this is 5 nanometer. So spot size is better for field emission. So in the current times, the most of systems are using the field emission guns, and they have the better resolution. So this is the table of the different types of the guns are being used for these systems like tungsten. What is the source size? Then LeB6, lithium hexaboride, Schottky field emission, cold field emission. So this is the source size. Then how much temperature they generate. Then about the brightness is what, and energy spreading across the beam. So these are, and the probe current, how much is there, and their gun vacuum, that how much vacuum is required in these guns. So in Schottky and this, they have the 10 to the power minus 9 torr or 10 to the power minus 11 torr. So for that a separate, a vacuum system is attached with all the microscope, because and their turbomolecular pumps, they are generally used. They can produce that much level of 10 to the power 10 or 10 to the power minus 10 or 10 to the power minus 11 torr order of the vacuum is produced in these columns. So why the vacuum is required? You see that vacuum is required. This is because that if the column is in a gas filled environment, means if there is no vacuum, so naturally there may be some air maybe, or some other environmental gas maybe. So once the electron beam is being formed by the electron gun, so it will get scattered by the molecules of air or some other environment. And because of that, the beam will be scattered. So it will affect their stability and intensity. The beam will not be scattered. We have to make them focus. So therefore the column must require the vacuum. Otherwise, you will not get a focused beam. It will be scattered by the molecules of air or other environment. Second thing is that if there are some other gas molecules, so these gas molecules, they may condense on the sample as well. So if they may condense on the sample, so naturally they will affect the contrast of your sample, and as well as also give the wrong information. Some other molecules may be deposited on the surface. So they were not the actual feature of your sample, but these molecules are deposited via the environment molecules, they are present in the column. So therefore we need the vacuum. So there must be a vacuum in the column to run these systems. So then, so that we can get a better image and we can get a clear image of your sample and from the surface. So therefore it needs and required a high order of vacuum in these systems. So now these are some lenses, you know that they are being used. Condenser lens, they are used for focusing the electron beam. Objective lens, the final probe formation, that how it should be highly focused, and then condenser lens. So they are being used for that. These are the objective lens, and these lenses control the final focus of the electron beam by changing the magnetic field, and the crossover image finally that can be magnified up to 10 nanometer. Objective lens, they change the current in the objective lens to the focus length, and that is a raster pattern. So there are some scanning coils. So because electron beam, so electrons, they are negatively charged particles. So we can get their movement by changing the electromagnetic field. So this electron beam that could move, it could move, just can scan, but not a very large area, but a very small area that can be scanned. So once if you are taking, you have to take the image of your sample. So you have to find out that the area which you want to scan it. So that area you have to find out, and how you can find out the area. So you can see the different area of the sample. So thing is that this probe is also moved, but very smaller in the micrometer range. So then we can change the position of our sample. So there is a provision in the system. Your sample can be moved in X Z direction, even X, Y, Z in all 3 directions. So you can change the different area of the sample. You can check. So that will give you either your sample is uniform or not uniform. If it is showing the same kind of morphology everywhere, it is a uniform sample. If it is not uniform, so somewhere you may get some different kind of morphology, somewhere may have the different kind of defects and uniformity. So that kind of things, you can check it point by point, scan your sample. So there may be a slight deflection could be done with help of these the scanning coils. It will move the electron beam position. So that scan coil and that pattern, you can change it with this coil. So these are some electron detectors and they are being used, and these are the sample stage. So this is inside the chamber. So here is the objective lens and all that. So these are EDX detector. EDX detector is basically, this is for elemental analysis. So you have to analyze the elemental composition. So this is energy dispersive X-ray analysis. You can detector is there. But for image production, there will be the backscatter detector or secondary electron detector. So these 2 detectors, these the scattered electrons, they will particular range of energy. As I told you that secondary electron, they have up to the 50 electron volt energy. So they will be enter into the secondary electron detector and greater than to backscattered. So then they will be used to generate the image of our sample using these this. So that is how the image will be formed. Image formation and magnification of the scanning electron microscopy. This is our specimen. Electron beam fall, then secondary backscattered electrons comes out from the surface, and then they will be they pass through the detector, they will amplify, and then they will send to the CRT, where the image of your sample will be produced. And we can see the image of this cathode ray tube in a scanning electron microscopy. So this is the summary of the main difference between the scanning electron microscopy and a transmission electron microscopy. So type of electrons that scattered, they are scanning electrons. Transmission electron microscopy, here we use the transmitted electrons. These are how much voltage you apply at the anode. So in SEM 1 to 30 kilovolt, but in TEM 60 to 300 kilovolt. So naturally we are applying high voltage in TEM. Why? Because the electron beam must be transmitted. So naturally it should be highly energetic. So voltage must be high. And if this voltage is high, so naturally their resolution will be better because the wavelength of electron will be smaller. So the specimen thickness, I told you that SEM does not matter what is the thickness, because we are not transmitted the electrons. They are coming from the surface. So any thickness can work for the SEM, but TEM, the thickness should be typically less than to the 150 nanometer, so that highly energetic electron beam could be transmitted across the sample. Magnification, if we see that it will be 1 to 2 million times, it can magnify the image, but in TEM it is more than 50 million times. So naturally the resolution of the TEM is better than to the SEM. And then this is the spatial resolution. Image formation, electrons are captured and counted by detector, image on the screen. Here the direct image on the fluorescent screen is obtained. Operation, in SEM little or no sample preparation required. You can directly put your sample, no thinning etc. required, so that is easy to use. While in transmission electron microscopy, you required a laborious sample preparation. Firstly, you have to make your sample thin, and as much as then it will be thin, then you have to put it in the microscope for generating the image. So that is the sample preparation part is tough in the TEM as compared to the scanning electron microscopy. Now we can see some of the images of SEM and what kind of information we get from these images. So this is the, you can see, this is the first image. So you see that there are some particles can be seen. So these are there. And you can see that particles are not uniform in size. Some particles are smaller, some of them are bigger. So particles, they are not uniform. That is the first thing. Even they are not well connected. You see that there are different gaps among the particles. So that can be seen. Shape, you can see that what kind of shape of this particle. So that is not, even this is irregular. They are not completely spherical. So some irregular shape is there. Somewhere they are being seen like a hexagonal, but not all, some of them. So that information is coming. So, and over there you can see here this something is written. It is written here 0089. This is the number of this image. They are being recorded. And 35 kV. This is the accelerating voltage. It's being applied to make the beam. So 35 kV this SEM is running to get this image, that this information is there. Then X10000. So this is means 1 lakh time. This is the magnification. This image is magnified 1 lakh times. So that is the magnification is given. And then here this is 100 nanometer. 100 nanometer, this over there is a bar. A bar is there. So this bar is equivalent to the 100 nanometer. And how this bar is generated? This is generated as per this magnification. How many times this image is magnified? 1 lakh time. So accordingly, this bar is optimized. So this bar is equivalent to how much? 100 nanometer. So a length scale is given to you for your reference so that you can measure the size via the magnification. So suppose I have to measure the size of this particle, that how much is the size of the particle. So how you can measure? Firstly, you measure this bar. Okay. Suppose this bar is 1 micrometer. So this is suppose the 1 centimeter. So you could say that 1 centimeter is equivalent to the 100 nanometer. And suppose this particle size is 0.5 nanometer, 0.5 centimeter. So 100 nanometer is equivalent to 1 centimeter. So then 0.5 centimeter will equivalent to the 50 nanometer. So by that way you can calculate the size of the particles. So size of the particles can be calculated with this approach. So that is, this bar is basically give the information about this. This bar is giving the information about this this length of the scale. So that is very important to measure the size of your sample. So, and this WD12, this indicate about which detector you are using. That second electron detectors, that information of the detector comes. So with this image, a lot of information you can get it. You can see that what is the size of your particle or grain. So that you can calculate by using this bar. So this bar is 10, as I told you, this is 100 nanometer. So accordingly, if this is half of this, it will be 50 nanometer. If it is double of this bar, it is 200 nanometer. So a reference is you get through this, that this length scale is up to 100 nanometer. Now you can measure this size and then you can calculate the grain size by using this image. So this is the scanning electron microscopy image of a sample. You can get it, and then you can have this sample cannot be called uniform because there is no uniformity, not in size, not in shape. Somewhere size is very smaller, somewhere size is bigger. Shape is even, somewhere is rectangular kind, somewhere is hexagonal type, somewhere is spherical types. So that is also irregular. So that, and even they are not well connected. There are a gap among the particles. So the porosity is there. So that kind of thing is you can calculate. So even this image you can see that there are some written 99.1 nanometer, the diameter of this particle. So even either you can do this manually, this way I told you that how you can measure the size manually, but even by the software or even itself in the system, you can also measure the size. There is some image J software where you can measure the size, or either in the systems, even in the SEM, you can measure directly the size. So you can just select the length or this to this way, it will give you the size and it will be marked over the grains. And you can see that these grains are having the better uniformity as compared to this one. Size is almost same, most of the particles. So their uniformity is better. So this kind of the better uniformity you may get with these scanning electron microscopy. This is another image of these scanning electron microscopy. So again, they are very uniform size in the size and shape. They are uniform grains. Almost all are having with the same size and the shape is same. So that is a uniform sample is being prepared. Their connectivity is better, porosity is less. So that information is coming. Again, this length scale is 1 micrometer. So you can see their size. It may be around 500 nanometer. This is the diameter of these particles. So that kind of information you are getting from this image. Similarly, this is the image of another material. It is porous. This is porous material. You could see that these are the pores. So that kind of materials are being used for some this specific purpose. That this is the like in battery materials, and then so they must be porous in nature. So accordingly they are prepared. You can see that how much is the pore size. So that information comes again on the bar. They are SE1 scanning electron detector is used. 15 kV voltage is applied. X is 35,000. This image is magnified. This bar is 100 nanometer. WD 6.8 mm. This is the distance of the detector from the sample. So that kind of information you can get it. You can see that the images you get for these the scanning electron microscopy. We also can see these are some of the TEM images. So TEM images is you see that this is a powder sample. You can see that these are the particles, and this length is given 50 nanometer. So 50 nanometer, this is this length of the scale. So you can measure the diameter of these particles. So the diameter of these particles you can calculate with this, and you can find out that how these diameter of the particles you may calculate for these particles. So these are the TEM images where you can see the diameter, and this diameter of them, they are very uniform particles. It is, they can be seen, and you can see this is the image. This is a high resolution image of a transmission electron microscopy. So they are basically, they are atomic planes. You see that how there are a very small kind of the lines. So what is there? They are the atomic planes. So these are the atoms, and these atoms, this is one plane, that this is another plane. So these are a very, very fine the particles you can see with that. So these images and this bar scale is 2 nanometer. This length is 2 nanometer. So, and you can see that this distance in one atomic plane to another atomic plane, it is very smaller as compared to this bar. So it is at angstrom level. You already know that atomic plane distance D, that is in the order of 1 to 2 angstrom. So that much is the range of the interplanar spacing. So even the interplanar spacing you can measure by the HEM, the HRTEM images, high resolution transmission electron microscope. So these atomic planes, you can see that with help of these transmission electron microscopies. So this is the high resolution TEM image of a sample. Even you not only get the image by the TEM, you also get the diffraction pattern. So that only you can switch the imaging to diffraction through the objective lens. So you can know that either sample is polycrystalline, either it is highly crystalline. And again, you can measure the interplanar spacing and these other parameters about the crystal structures. So that kind of information you may get from the transmission electron microscope. So TEM resolution is very, very better. You can see even you see that if I magnify this image, so it will be, you can clearly see these atomic planes and difference in these, how much is the distance of the angstrom level in these atomic planes, and even atoms can be seen. So that is the TEM is a very versatile tool, and it gives the very high resolution image of the atoms molecules. And you also can get some other information from there. So this is again the image of a scanning electron microscopy. It's again a porous material. So you can see the pore size you can calculate. And again, there is information. High voltage is 4 kV, spot size is 2, and the distance from the detector to 7.7 mm, magnification 30,000 times, pressure, that is the pressure inside the column, means the vacuum. So the surface morphology structure, you can get it from the scanning electron microscopy images with help of this. So these are some of the images that do the high and low kV. So naturally the kV here is high, here is the low. So kV will be high, so resolution better, feature size will be clearly seen. So we can see this image is having the clarity as compared to this one. Similarly, these are this is 30 eV and 500 eV, so that have the better resolution. And backscattered versus secondary electron detector. So the backscattered secondary electron detectors, their images are more clear to the backscattered because they are coming from the depth. So this is the image. And I also told you that there are you can also do the elemental analysis by using the EDEX detector, okay, attached with the system. Energy dispersive X-ray analysis you can do, and you can get this kind of the EDEX spectra. On the y-axis there are count per second, and on the x-axis you have the binding energy in keV. So every element have their own binding energy. So it may be that binding, as per the binding energy, you can identify this is which one element. Either this is copper, this is cobalt or zinc, whatever. So as per the binding energy, you can identify that which elements are present in your sample, in your composition. You can define with help of the EDX spectra. So thank you for your kind attention. This is about some of the idea about scanning and tunneling electron microscopies.
Thank you very much, sir, for such a nice presentation. Kyle, I ask you to moderate the session, please.
Sure, ma'am. So very good morning to everyone, and wonderful session, sir. Really loved it. Sir, most of the questions have come to us on YouTube, and thus I will be asking the first question as what is the minimum thickness for a sample for TEM? What is the minimum thickness for a sample for TEM?
Yes. So it will be less than 150 nanometer. That must be the thickness of your sample. However, it will also depend upon how much is the energy of the beam. So If it is highly energetic, so it will depend upon the voltage, how much we applied. But even for the 300 kilovolt, if we are applying as a voltage, so the thickness must be less than 150 nanometer. So as much as thin, it will be better. More electrons will be transmitted and you will get a better image.
Okay, so very next question is how to calculate energy levels using dark field TEM images.
Sorry?
How to calculate energy levels using dark field TEM images.
Dark field TEM images, we directly cannot measure the energy levels, but some of the parameters we can calculate the distance among the atomic planes and the distance between the atoms. And on that basis, some idea and information can be given about the energy levels.
Okay, I'll just ask one more question to Sir, and that would be, so which types of columns are used in SEM? Which types of columns are used in SEM?
Which type of columns?
Yes.
Column is basically, this is the outer chamber. Inside that, all the assembly are being placed. So this is a stainless steel chamber of the column. Because vacuum has to be created, the material we use, that it could not have the corrosion with vacuum and not have the degrading property with the vacuum. So that kind of materials are used in the in the chambers of these SEM.
Okay, sir. I would just like to ask you, sir, one thing, because we are having limited questions. So could I give your email ID to the participants so that they could contact you with their queries further? Would that be good?
Yes, email ID, you can note down that Anurag, TPH, @nitkkr.ac.in. ANURAG DPH. D for department, PH for physics, @nitkkr.ac.in.
Great. I think we will also put the email ID on the Zoom chat as well so that you can all connect with Sir.
Please share on
we will take on these questions for you. You can ask these questions to Sir on email. Thank you, everyone. Abhilasha ma'am, over to you.
Thank you, Kyle. Now I invite Dr. Nikhila to express his gratitude, express the gratitude for the sir. Over to you, Nikhila.
Thank you, ma'am. Thank you, Kyle. Good morning, everyone. Well, that was quite an intriguing session, sir. I hope you all would agree with me. Indeed, sir has quenched the thirst of our knowledge in the field of sophisticated instrumentation, starting from their history, working, comparison between TEM and SEM, to balancing between the theoretical aspects till the pinnacle of advanced instrumentation techniques. The lucid explanation with relevant day-to-day examples and their applications has only inspired us to delve further into the topic. On this note, I, Dr. Nikhila Bhatt, on behalf of the Department of Chemistry and all the participants, would like to express my sincere gratitude for keeping us engaged throughout the lecture on SEM and TEM. I'm quite sure that the participants must have been highly benefited and their passion for research must have been rekindled once again. Thanks, sir. We now break for 15 minutes. However, do not leave the session, participants. This interaction will continue back from 11:35 a.m. sharp as we await for an enthralling live demonstration of the instrumentation techniques by Anurag sir, followed by session 2. Thank you.